Okay, so in this video we're going to talk about measurements. So when we talk about measurements, we use the terms accurate and precise. Now a lot of people will actually use these two words interchangeably, but they're not interchangeable. They do mean different things. So accuracy is how close you are to the true value. So how correct are you? So if you measured something and it's supposed to be 5 grams, did you measure 5 grams? How close did you get that? How close were you to the actual measure or the actual value of 5? Precision is going to be how close a series of measurements are to each other. So essentially, if you take a series of measurements, let's say that we get 5.0 grams the first time, and then we get 5.1 grams, and then we get 5.10, those are pretty precise. So they are pretty close to each other. Now, if we also looked at different measurement, let's say that we have like 5.10, and then we have 5.13, and then we have 5.15. Well, I would still say that all these measurements are very precise. They're very close to each other because look, the first and the second digit all match each other. They all vary with that last digit, and that when you take a measurement, that can be something that varies from person to person or from measurement to measurement. So precision is going to be how close these series or these measurements are to each other. So accuracy is essentially how correct you are. Precision is how consistent you are. So accuracy indicates how well you performed the lab, and then how well the lab equipment performed. And then precision is going to be if you can do this over and over again and get the same results. Okay, so can you be accurate and precise? Of course. So if we take an example of a knife thrower, the knife thrower's goal is to not kill the person. Well, he hit the board, so he did not hit the person at all. So that was the goal, that was accuracy. And then he hit all in the same area. So he hit this one area, so he was precise. So can you be not accurate or precise? Yes. So again, the goal is to not kill the person. That obviously did not happen here. He hit this person all 3 times. And he was also not precise because he threw in completely different areas. So this would be if you did a lab 3 times, you didn't get close to the actual value, not one single time, and your results were not close to each other. So the series of measurements were completely different from each other. So can you be precise but not accurate? Yes. So right here, the goal is to not kill the person. That obviously happened here. And precision happened because it all happened in the same spot, which looks a little suspicious. But when we're talking about a lab, or when we go perform a lab or we're trying to collect something, how does this happen? Well, essentially, one of 2 things happened. One thing that could have happened is that you did something very wrong in the lab over and over and over again. So there's something inherently wrong with your procedure. Something is wrong with what you're doing in the actual lab. The other thing that could happen is you have a measuring device that's not calibrated correctly. So maybe the device consistently measures 1 gram too high or 1 gram too low, or etc. So that can definitely happen. Okay, so how do we measure accuracy? We measure percentage of error. So percentage of error compares 2 numbers. The experimental, okay, that's your value. That's what you go get in the lab. So when you write down numbers and then you make a calculation, that's your value. The literature value is what you should have gotten. Okay, that's what the actual answer is. So if I tell you to go and collect 2 grams of a substance, your accepted value should be 2 grams. Your value is how much did you collect? Did you only collect 1 gram? Did you collect 1.5 grams instead? Okay, so let's look at an example of calculating this. A student determines the density of a substance to be 1.40. Find the percentage of error if the accepted value of the density is 1.36. So, okay, the accepted value is 1.36. That's what the student should have gotten. Okay, so that's my literature value. my 1.4, well, that's what the student determined, so that's your value. Okay, so that's the experimental value. So at this point, we can just plug those numbers in. So 1.4 is my experimental value. I'm going to subtract 1.36, which is the actual, and then I'm going to divide that by the actual. Now, in the formula, there are these brackets. That means absolute value. You shouldn't have a negative percentage of error. That doesn't happen. So just make your value positive. So now you're going to take the difference and then divide and multiply it by 100 because it is a percentage, and you should get 2.9%. So for us, for your lab purposes, anything less than 5%, I'm very proud of you. So the lower you can get this number, the better you did in the procedure, the better you did with the actual lab. Okay, so when we take measurements, a lot of people actually take measurements incorrectly. So when you're taking measurements, okay, the number of digits that you actually have in your measurement is determined by your measuring device. You cannot just have 3 decimal places on your measurement because you thought that's what it was. Your device determines how many digits you have in that measurement. Okay? You can estimate 1 digit beyond what your device can read if the dash or the measuring line is the smallest amount for that place value. So let me look at a paper clip down here. So we've got a paper clip. I'm going to measure that. Okay, so I can see that the paper clip is definitely beyond the 2. I am certain it's at least 2 centimeters. But then if I look at the middle, I've got these little dashes. So it goes from 2 to 3. There's 10 in there. So this should be 0.1. So 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, and then I get to 3. So each of these little dashes represents a 0.1. So I'm definitely sure it's at least 2 centimeters. I'm also pretty sure, let's see, yeah, I can be sure that this is going to at least 2.3. But if I look closer, it looks like it's a little bit past that. So I'm going to estimate 1 more digit and say, well, I think it's 2.35. So you can be certain about the 2 and you can be certain about the 3. The last digit will vary from person to person and measurement to measurement, okay? So if the smallest dash here, okay, is the smallest amount, then you can estimate 1 more digit. You should have 2 decimal places here. So 0.1, if I go any lower than 0.1, it's 0.09, which has 2 decimal places. So that's why I know I can estimate 1 digit here, okay? Now, can you do that with every measuring device? No, it depends on what it goes to. Okay, now, why do we care about this? Well, we care about this because it indicates how precise your measurement is. And when you're reporting data in a science, in some sort of scientific manner, that precision, how precise your data is, it does matter. Okay, so the digits in a measurement are going to show how you will take that value and use it for a calculation. It shows precision. It shows how, essentially, how good your measurement is. Is it the only parameter of good? No. I want to look at the accuracy too. Okay, but let me show you another measuring device. So these are 2 graduated cylinders here. So the one on the left has 1 milliliter ticks and also 0.5 milliliter ticks. So if I look right here, this is the 15, this is 20. So this right here, this will be 16, this will be 17, 18, 19, and then we have 20. So the lines in between that would be a half. So 0.5, then 1, then another 0.5, and so on. Okay, so my smallest dash is the 0.5, okay? I cannot report this as 0.50 or 0.55. I can't do that, okay? Because if I go below 0.5, well, I can be 0.4 or 0.3. I don't go to 2 decimal places there. So my measurement can, if it's below the 0.5 line, it can read somewhere between 0.1 and 0.4, if 0.5 if it's on the line, okay? And of course, when we're reading a graduated cylinder, there will be liquid in there, so it'll curve down, and then we're going to read at the bottom of that curve called the meniscus. Okay, now, if the meniscus happens to be above the 0.5, the measurement can read between 0.6 and 0.9, and if it goes up to the 1, you read it as the 1, or 1.0. There shouldn't be two decimal places there. So how you report a measurement, it does actually matter. Okay, so if I'm looking at this one, I have 1 milliliter marks, and then I have 0.2 milliliter marks. So if I'm looking right here, here's my 8, okay, here's my 9. So we've got 5 ticks in between, so it has to be 0.2, 0.4, 0.6, 0.8, and then we get to the 1. So when you read this, okay, if your meniscus falls right on a 0.2, a 0.4, a 0.6, a 0.8, that's what your measurement would end with. Okay, if it's slightly above or slightly below one of those ticks, your measurement can end with 0.1, 0.3, 0.5, 0.7, or 0.9. Essentially, it should be in between the two ticks. So if this is 0.2, if anything is below that line, it could read as 0.1. If it was above that 0.2, it could read as 0.3. If we were above the 0.4, it could read as 0.5. But you should not have two decimal places here, because 0.2 is not the smallest. 0.1 would be the smallest before you go to two decimal places.